Okay, the second example, again, you can cut and stick. This time we've got a machine making bolts. And we know that the bolts coming off this machine are normally distributed, and their diameters are normally distributed with that mean and that variance. How do we know that? The great god of statistics has told the person making the question. Okay, we just don't query that at the moment. After this machine has been serviced, a random sample of 50 bolts is taken to see if the mean diameter has changed. We assume the standard deviation is still the same. The mean of the sample is less than what was up here, and we're now told to see at the one significance level whether the mean diameter has changed. So you've all got that question in front of you, so I'm going to take that off the screen. Right, what was step 1 of our 6-step rule?
Write down H naught and H1.
Write down H naught and H1. Yeah, okay. So, what is H naught in this question? H naught is always the status quo, nothing bad has happened. So H naught is?
Mean diameter hasn't changed.
Yeah, the mean diameter hasn't changed, so it's unchanged. Mean diameter, is unchanged and remains at 0.580 centimetres. And in stat speak, in other words, mu equals 0.580 centimetres. So now we are looking at H1. You need to look at the question carefully. What will H1 be?
Mu does not equal 0.
Yeah, it just says test whether it's changed. They're not interested in whether it's got bigger or smaller, they're just interested in whether it's changed. So H1 is the mean diameter has changed. So in other words, mu is not 0.580 centimetres. Is this a one-tail or a two-tail test? It's a two-tail test. So at this point I would just do a quick sketch. We are looking at here the diameters. Under the null hypothesis we have 0.580. Two-tail test, so we're going to look at two tails here. A less than tail and a greater than tail. Now, step 2 was the significance level. What significance level are we told to use in this test? Significance level of 1% we were told to use. So that 1% has to be split between these two tails. So that tail there is going to be 0.5%, and that tail there is going to be 0.5%. So that our tails together are their 1%. So in this question we're going to have two critical values to find. One over here, which I'll call C1, and one over here, which I'll call C2. And if the sample's diameter is in one of those tails, we will conclude that H0 is false and we will accept H1. If our sample diameter is in the middle bit, then we'll say it's absolutely fine, we'll accept H0, nothing's changed. Tom?
Would you need to calculate both critical values?
Why are you querying that?
Because we have a statistic that's 0.577, hence it can only be the lower one, not the higher.
You're quite right here, yes, okay. And there was another reason I thought you might be asking that. What's another sort of reason?
That they're going to be the same at the opposite side view.
Sorry, it's the...
Because they're equal distance.
Yeah, that's right. There's symmetry involved here as well, yeah. If you know that that is 0.6, which is 0.02 above it, then you know this one's 0.02 below it, it's 0.56, whatever. So yeah, there's symmetry and things in there you can use. So, step 2 was the significance level, which we said is 1%. We've done our diagram. Step 3, calculate the critical value in the critical region. So, we're on to that step 3 now. Okay. Now, we are going to use the distribution of d bar and this will be normally distributed, and it's always mu sigma squared over n. Well, from what we're told by the great god of statistics, under the null hypothesis, that mu is 0.58. You always there use mu from the null hypothesis. Okay, it's always mu from the null hypothesis that goes in there. The standard deviation we're given is 0.015, so that's the standard deviation. That's the variance, and we are always dividing by n, the size of our sample, which was 50. So that is the distribution we're going to be using for D bar. Yep.
When would you actually ever use this? Where was it actually?
For trading standards for quality control purposes is when it would be used. Okay. So, to save you a bit of time, I'll tell you that over here comes down to be... Actually, I can't tell you what that is. I haven't actually worked it out. 4.5 times 10 to the negative 6. Okay, thank you. Right, so Tom's already pointed out that the sample statistic is lower than this mean. So what we are going to do, first of all, is find C1. That critical value on the left is the one that we're interested in. Well, we know that the probability of D bar being less than C1 is going to be 0.5%, which is a decimal is 0.005. So if we go into our phi notation, it's going to be at C1, our critical value, minus the mean over this sigma squared over n square rooted, which you've already told me is that number up there. And I'm going to put that equal to 0.005. And just like last time, what's the next thing to do once we've reached that stage? Anti-phi, yeah. Which on the left-hand side is just taking away the phi. I got anti-phi 0.005. Now that's where the problem comes. You can't anti-phi that. So can anybody remember, anti-phying a small number, what do we do? Negative anti-phi of 1 minus the small number, yeah. So that's negative anti-phi of 0.995. 0.995 again is in the bottom of that green table. 2.576 is what somebody said, and that's right. So now it's a case of rearranging that equation, that left-hand side and that right-hand side, and you should be able to work out what C1 is. Anybody got? 0.5745. Yes. Okay. So, what I've done here is just put that on my diagram. I'm going to cover that one up for a minute. We've got our two tails here. As somebody said, by symmetry, you can work out the one on the right. If you work out that gap, if you do 0.580, take away the lower one to work out that gap, and then add that on to the 580, you will get that value there, purely by symmetry. Okay?
How about 0.585? Can I get 0.745?
Which one are you up? That one there, that's...
Yeah, I didn't get that. I got 0.585.
Did you square root up in the bottom of the thing? Because that is correct.
You did remember the negative 5 when you changed the by.
What did you get, Billy? 5855?
Oh no, you're right.
Okay. So, we've now worked out then our critical regions. Okay, our critical regions are as follows. Our critical regions are if the diameter is less than 0.5745, or if the diameter's mean is greater than 0.5855. If it's in those regions, then we will reject H0. If it's in a critical region, we will reject H0, which means we will have no option but to accept H1. But what was our step 4, the test statistic? It was given to us. What was the test statistic? 0.577. It was in here, isn't it? The test statistic we were told is 0.577, which is not in the tail. So we will not reject H0, we will accept H0. So step 5, the decision, we will accept H0 because our test statistic was not in the tail, or either tail. The test statistic D bar, which was 0.577, was not in a critical region. And then step 6 of putting it into words. Now I'm going to write this one out slightly more fully because we should really mention the significance level of what we're doing. So we can say that we conclude at the 1% significance level, because if we use a different significance level we might come up with a different conclusion. But at the 1% significance level we conclude the mean length is unchanged. i.e. mu is still 0.580 centimetres. Are we happy about that process? So your homework is cut and stick what you need to, including example 3, because that's what we're starting on next lesson. Okay?